Swayam Prabha. Digital India. Educated India.
Let's continue our discussion on convergence of sequence of random variables. We have talked about different notions of convergence. In the last class we looked at Cauchy criteria. What is the other thing we looked in the last class other than Cauchy criteria? So we looked at some other means of other conditions or other properties that one can verify to check whether a sequence converges to a sequence to a limiting random variable, right? One was this correlation property of the random variables. So we move on now, like we want to now study, fine, we have a sequence of random variable, whether they converge to some limiting random variable. So often instead of looking at the random variable itself, we may be interested in looking whether the means of this random variable converges to some value. So when I look at the means of each of these random variables, right, I will end up with a deterministic sequence. After taking expectation of each of this random variable, I will have a deterministic sequence and it converges. So and if it converges, now I want to understand when the mean will converge, okay, or are there any property that will help me to infer from the properties of convergence of the random variables in other what we have already studied, like convergence in probability. So let us say that I have xn converging to x in probability. Okay. So what does this mean? This means basically limit as, sorry, so this basically we said the probability that is equals to 0. Now suppose if this happens, can I say that expectation of xn goes to expectation of n's? Or what I am basically asking is, so what is x here? Expectation of x is nothing but expectation of limit as n tends to xn, and this limit is in what? In the probability sense, whether this happens, or what I am basically asking whether this is the same as limit as n tends to infinity of expectation of xn, right? When I said this is what exactly I meant, right? Whether expectation of xn converges to expectation of s, this is basically saying whether expectation of n as n goes to infinity is equals to expectation of xn. Yeah? Yes, we have said, but we are doing this, we are asking this question, right, whether this holds. We are not right now saying that this is true, we want to see whether this holds. If at all it holds, when does this hold? Okay. So when we studied some examples, when we are studying convergence of random variable in probability sense and the mean squared sense, we came across an example where it said that it converges in probability, but it didn't converge in mean squared sense, right? We had an example like that, because convergence in probability does not always imply convergence in mean squared sense. That happened in that example because it so happened that even though the example I had there, xn's, they are putting values on a smaller and smaller intervals as I put n goes to infinity, but their amplitude was also exploding. So you remember, like we had this example where, so it was like this, and this was some sequence, what was we called it, an. As n increases, this was putting on a smaller interval, but it was amplitude is also increasing, right? And we had argued that unless an grows much smaller than n, this guy will diverge. I mean the mean squared error will diverge and this will not converge in the mean squared sense. So similar behavior happens here, like that is what we want to capture. If you are looking at the expectation of the random variable, even though it may be putting mass on a smaller and smaller interval, but it may take a very large value, right? Even though because of that it may converge in probability sense in this fashion, the limit and this may be almost same everywhere except for a small interval differing by epsilon, or like they may be different at only some small interval, but on that interval my xn may be taking a very large value. Because of that, expectation could be very large there, and in that way we can't say that always this kind of behavior happens. To make this more concrete, let's look at an example. So let's say u is a random variable. Okay, now I'm going to such that so let's say I have a random variable u, I have a sequence of AIs which are events, and these events are such that their probability goes to 0 as n goes to infinity. Okay, and I am also going to look at this sequence bi. These are another set of sequence of numbers, some numbers that are given to me. Let me see, and I am going to assume that they are non-zero. So this is I am starting with, and I am going to define a sequence of random variable based on this in the following fashion. So this u does not depend on any n, it is just like one random variable u. I am going to define for each n a new random variable which is the sum of these two random variable u, and this bn is a deterministic quantity which is coming from this given sequence, and it is multiplied by this indicator function which depends on an, and an is the event that I am assuming it will be such that its probability goes to 0. Let us say I have such a setup. Okay, do you understand what I mean by indicator of an, right? Fine. Now if I am going to look at its expectation, what its expectation is, and I will also assume that with finite mean. okay, plus what is this, what will be if I take expectation, this will be Bn into, it is going to be Bn into expectation of the indicator function, right. What is then, it will be probability of An. So it looks like its expectation for any n is going to look like this. So now let me ask this question. I have a sequence of random variables like this. Does this converge in probability? So to verify that, what I need to do? Probability that what you guess it should be converging to, if at all it converges? U. So let us say our guess is, let us assume I am going to take to be U. What is this quantity? If I can show that as n go to infinity, this probability goes to 0, then I know that xn converges to U in probability sense. Now check that or see that this probability is same as xn is not equals to U. See, when I say xn is not equals to U, right, that means the difference is going to be some non-zero quantity. So it could be either greater than epsilon or it could be much greater than that, right. That is why this is going to be an upper bound on this, fine so far. Now come back to this. Now what is the probability that xn is not equals to U? It is going to be so probability that xn are not going to be equals to U, that is enough that if this quantity happens to be positive, right, then there is going to be different, and when this quantity is going to be positive, when this is true. And what is that probability? That probability is nothing but the probability of event An, right. So the way I have constructed this, xn not equals to is nothing but probability that of An. So the probability that they are not differing is that this quantity is going to be positive, this quantity is positive, is nothing but this An has to be, this indicator function has to, this condition of this indicator function has to satisfy, and that is going to be satisfied with probability An. And what is our assumption? We have said that I will come up, my assumption is such that this An is such that this guy goes to 0. Okay. So then what we have shown then? So what we have just shown is that xn converges to U in probability sense. Okay, now let us come back to this. So if xn converges here to U in probability, fine. Now I wanted to ask the question, can I also do this, and can I also say that expectation of xn converges to expectation of x in this case is going to be U, right, because that is the limiting distribution. But here if you focus on this, even though this probability of Ans are going to 0 as n goes to infinity, I could choose Bn's such that this product does not go to 0, right. So in that case this expectation of xn need not be the same as expectation of U as n goes to infinity, right, they can be different. So as you see that even though xn can converge to some distribution in probability, but that does not automatically allow us to take expectation of the sequence to be the expectation, the limit of the expectation of the sequence to be the expectation of the limiting random variable. So then the question now is, when does this happen? right. We want to now look at the conditions when does this happen. Yeah. Yeah. So indicator of an event, expectation of indicator on of event is what? Is the probability of that event itself, right? How can you write this? Just write it into 0 and just expand it. So expectation of this. Only the one term remains, the other term is 0, and the one term that remains is exactly this 1 into PR of A. This one? Let us look at this event xn not equals to u, right. That means the difference between them is not 0, it is other than 0, it could be positive or negative. When you are going to look at the absolute value, that is going to be, the difference is going to be greater than 0, right. What you are saying, all you are asking is this difference is going to be greater than 0. That could be either greater than 0, greater than epsilon, or it could be much more than that. Exactly. So this event is going to be a subset of this event, that is why I am going to get an upper bound. Fine. So then I am going to now state couple of results which actually helps to do this kind of interchange. What I mean by interchange is exactly this. The first one is called bounded convergence theorem. See, some of these results you may not be able to directly relate it to where they come in practicality, but some of these results are useful to state some results, some of that you are going to see later in the class today, that gives us very practical, gives us some intuition about some of the practical things. So these are like some intermediary building steps that we need to understand to understand some larger result. For example, later in the class today I am going to talk about central limit theorem, that is one of the important result and which has many practical implications. So to understand that we have to understand these results. So at every result do not try to connect it with practical things, then you may be lost, but just try to follow what we are trying to define and then eventually where we are going to connect it. Okay. Let this be a sequence such that there exists some L So this theorem gives us the first condition. It says that suppose you have a sequence and such that you have some L which is finite and all my random variables, their absolute values is bounded by this random variable with probability 1, then convergence in probability to a random variable x implies that their expectation of the sequence of random variable converges to the expectation of the limiting random variable. So this is this is a very intuitive statement, right? So that is why it is called bounded convergence. What you are saying is your random variables are always bounded, okay. That naturally means that even your limiting random variable can't be unbounded. So if you have everything bounded, then there is nowhere that in the sequence you will incur a case where something explodes, right. So because of that, there is nothing observed behavior when I have this boundedness and everything goes well. Okay, let's look into quick proof of this. So when I make this kind of assumption that all the random variables are bounded like this, where I made such case again, did I use such an assumption earlier also? Where? Yeah? Yeah, so in which type of convergence I used it? In mean squared sense, right? When I had a mean squared sense, I wanted all the second moments of all the random variables to be bounded there. So if I have a random variable like this, and if L is finite, and if I take the second moment, will it be still bounded? And that limit is going to be what? Instead of L, it is going to be L square, right? So this condition, and I had, when I said convergence in probability implies convergence in distribution, but convergence in probability does not always imply convergence in mean squared sense, right? But I said that convergence in probability implies convergence mean squared sense under some condition. What was that? Yeah, so if all my sequences are bounded by some random variable. So here is it, can I say that here convergence in P already implies convergence in mean squared sense? Yes, right, because that Y is nothing but L in this case. And we have already said that just L square should be finite, right? Okay, fine. So, and we have already said that, so under this condition we know that if xn converges to x in probability, it already converges in mean squared sense. And in the mean squared sense, when I discussed it, I already said that the limiting random variable, its second moment is already finite. That was a consequence which I asked you to verify, I don't know you guys did. So that came from triangular inequality. So by the same logic, we can also say that here this x is going to be bounded, okay, its expectation is going to be bounded, right. So this is also going to be bounded. Now let's understand, so you can verify that, I am just leaving you this, that x is going to be also going to be L with probability 1, whatever that limit is. After this, let us focus on this inequality. Take any epsilon greater than 0. Now my claim is this x minus xn, I can write upper bound it in this fashion. So this is the main inequality I need to make this final claim. So let us see we understand this inequality. So take an epsilon greater than 0, if it is such that this x minus xn, this absolute value is greater than epsilon, greater than or equals to epsilon, if this is true, or like let us say this is not true, that is this difference is upper bounded by epsilon, this term is already 0, right, and then this condition is already true, like x minus xn is upper bounded by epsilon, that is what I have already assumed. In the other case where let us say this holds, okay, where x minus xn is greater than epsilon, it is going to be at least anyway epsilon, it is going to be plus something else, and what is that something else? We can always write x minus xn as upper bounded by x plus x of n, right, and both of them are upper bounded by 1 with probability 1, so I could write them as upper bounded by 2l with probability 1. Okay, so just verify, that is why I could write this will not be greater than 2l at most. Okay, I mean see like this x minus xn I could have already written this is upper bounded by 2l, but I am expressing in terms of this epsilon because this gives me a tighter bound. That is, if this condition holds, yes, 2l is there, 2l is there. If this condition does not violate, then epsilon is the bound, that is a tighter bound. Okay. Anyway, so I have this inequality here. So now let us see what I want. I want to find expectation So what is the meaning of expectation of xn goes to expectation of x? That means if I am going to look at the absolute difference of these expectations, this should go to 0 as n tends to infinity, or alternatively what I can show, if this is upper bounded by epsilon for some n which is sufficiently large, right, for all the n after some point. So now fine, this is there, this I could write it as expectation of x minus xn. Why I could do this? Because of the linearity of the expectation, right, and now I could do that. Now I have taken this absolute term inside the expectation. Is this true? Right, because the differences I have made absolute, so my expected value is going to be larger. Fine. Now I am going to bring in this bound which I have applied here. Okay. And what is this is going to be? So if I use this bound, this is going to be epsilon plus 2l and expectation of this indicator. So that is going to be right. Now I know that this guy goes to 0, this probability goes to 0, right, and I know that because of that then I can say that there exists some n naught such that for all n greater than or equals to n naught I can replace this guy by maybe there exists enough for all n greater than n, I can write it as this is going to be less than or equals to, I can always write it as, so you give me epsilon, I will take epsilon by 2l and I will look after which point this guy is going to fall below epsilon by 2n. I can always, there always exists such an n, right. So now if you do that for sufficiently large n, this guy is going to be, I can upper bound by 2 epsilon. This I know this guy goes to 0, right, as n goes to infinity, okay. Whatever epsilon it is, for whatever epsilon you are given, it goes to 0. Now what I will do is, whatever epsilon you give me, I will be looking at epsilon by 2l, and I know that after some n naught, this guy is going to be below epsilon by 2l. It is because this guy is going to 0, right. So I will just plug it this quantity here for all n which are greater than this n naught 0, then it becomes 2 epsilon. It is just like what? Yeah, you can take anything. I just want to bring it simplify in all this 2 epsilon. Now it is clear, right? Like now I am more familiar territory. Now I can say that, okay, I have shown that this difference is upper bounded by 2 epsilon for all n greater than n naught, and this n naught is a function of epsilon. And now this, if this holds, if I can do this for every epsilon, then what does this imply? This epsilon is arbitrary, right? So then this is exactly the definition that this xn converges to x. So this implies, so I am saying that this implies this. Are you convinced or not? So what I could show, okay, now think of this as this was an an sequence and this is the limit. What I have shown is an minus a is going to be upper bounded by 2 epsilon for n sufficiently large, and this I am giving for any epsilon that you have given to me. So that means that is what the definition of the limit, right, an converging to a, and I could do that because I am exploiting the fact that I already know that xn converges to x in probability. I am just using that convergence to claim that this guy converges. So fine. So this is one simple thing, like if I know that my random variables are bounded, and if that may, and my random variable converges in probability, then I can do this interchange of the expectations. Yeah, so what is the other things? When is where not necessarily, it is not on if and only if condition. If this holds, then we say we can do this, but if we can do this at all, I do not know, this it is that always implies that such a thing implies. So let us say these other things which tries to generalize this bit. See, when I tried to state this, I wanted this xn's to be bounded, right, and this bound was a deterministic bound, but you can relax this and say that instead of the deterministic one, I can have this bound with some using a random variable. So L I can replace by a random variable y. If such a y exists which always dominates xn, then also it is possible. So let me make that. So this is called So this is just a slight generalization of this bounded convergence. Instead of boundedness, now we look at domination. We are going to say that these sequences are such that they are all dominated with probability 1 by random variable y, and this dominating random variable is such that its mean is bounded, and then if I have this sequence converging to some x infinity in probability, then I can do this interchange. Okay. So it is same as this, except for the fact that I am replacing this L by this y which dominates the sequence, but that y I will further want that it has a finite expectation. So if I can find such a random variable which has finite mean and it dominates my sequence, and then I can interchange this limit if my sequence converges in probability. So we are not going to prove this, but just take this, like you should understand how to apply these results. So before you apply, you should better check all these conditions. So the last one, called monotone convergence theorem. So this is, as the name indicates, this is an analog version of monotone convergence. We already come across deterministic sequence, right? So what do we know about a deterministic sequence when it is monotonically increasing? So let's say I have a sequence, deterministic sequence, let's talk about deterministic case. If it is always increasing, like a of n plus 1 is going to be greater than or equals to a of n, what happens to limit a n? The limit exists, it converges. What? It depends on n, why? So any sequence which is monotonically increasing necessarily converges, right? Either to a finite one, or it could be like even the limit could be unbounded. At least it does not diverge, right? So if I have a monotone, let's say these are a1, a2, 1, 2, 3, 4 like that, right? And this is my sequence. If my sequence is like this, increasing, if it is increasing, that either it blows up and goes to infinity, or like it saturates at some point, right? So it always converges. So similar analog. So this is the convergence in the extended domain. So we allow the limit to be infinity as well. So it is not necessary that when we talk about convergence, the limit has to be always finite. Even the limit could be infinity, right? It is just like that. It is just that it does not happen that while it is going, like at some point I come down. So this violates the definition of my convergence, right? So if it is always increasing, at some point either it goes to infinity, in that case it is infinity is the limit, or it saturates at some point, then the finite, in that case that saturation point is the my limit. Okay, let me take this. I have this n greater than or equals to 1. This is a monotonically increasing sequence, right? Where does this converge? Converges. This is the extended notion of converges. Yeah? No, this is deterministic case also. I am giving you a deterministic case here, right? I have this n. Why like this sequence an? This an is simply n. This is converges, but it converges to infinity. Okay, fine. So I am now defining this sequence in this form. So I have my random variable sequence such that if you are going to fix a sample point, on that sample point this forms a monotonically increasing sequence. Okay, and then define my limiting random variable for each omega to be the limit of this. So now this xn of omega is a deterministic sequence, right? And since this xn of omegas are monotonically increasing, this indeed exists. Maybe it could be limit could be infinity. What is the term for that? With possible value of infinity. So if this happens, then I can always say my expectation I can interchange like this. And here I really don't need to first check, I don't really need a convergence in probability. If this monotonicity property holds, that's it. Like if I can check this, then I can always.
Infinity of omega becomes infinity.
Yeah.
What will be expectation of x will also be infinity?
Yes, but provided that sample point has non-zero probability. If that omega has 0 probability, even if it is infinity, that becomes a bit weird to define, right? Like this has infinity, but its probability could be 0. But in that cases, we have to define its value to be the product of 0 and infinity to be 0, and then we can continue with that. Okay. So fine. So these are the 3 theorems called bounded convergence, dominated convergence, and monotone convergence. You should know and understand when you can use them.